Good evening and welcome to what is a rather impromptu additional July Astro Talk. Tonight we're going to be treated to two amazing presentations. The first will be by Mike, and I'll get your name wrong, but I'll try, Skrutskie? Oh, Skrutskie. Mike Skrutskie, there we go. And Anne Verbiscer? Verbiscer, there we go. I'll learn eventually. But before we begin, I'd like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges traditional custodians of country throughout Australia and their connections to land, sea and community. And we pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. A quick reminder about our Sea Lake Astrofest. Tickets are available for accommodation and events. Don't forget the dot because I keep forgetting it, sealakeastro.asv.org.au, open to members and the public on the weekend of Melbourne Cup weekend, actually, long weekend. Now, straight into tonight's talk. First one will be by Mike Skrutskie. I'm going to keep getting it wrong. That was good. Mike is a professor of astronomy at the University of Virginia, where he directs a laboratory for the design and construction of infrared cameras and spectrograph for large ground-based telescopes. He was the principal investigator for the NASA NSF 2 Micron All-Sky Survey, a science team member of the NASA Wide Field Infrared Survey Experiment, WISE, and an architect for the Sloan Digital Sky Survey. Recently, he's been collaborating with the Australian astronomers in the development of a cubesat to study distant gamma-ray bursts at near-infrared wavelengths, and has been developing a near-space telescope that will fly to 30 kilometres plus altitude under a huge stratospheric balloon. That sounds interesting. Right, there we go. Welcome on. The floor is yours.
Switch on the microphone here. Give me just a moment to find the HDMI cable, but impromptu is our middle name. As Anne may tell you more detail, or as possibly as Peter Schottel has told you, we have spent the last 2 weeks, and we'll spend the next 2 weeks as well, traveling all over Australia chasing asteroid shadows. And honestly, it's being made up as we go along day by day. And okay, you may see nothing. Oh. Excuse me, let me try and get the screen swapped. All right, technology break for just a second, folks. Let's see if we can start from the first slide now. Now it's happy, good. And so I'm the warm-up act for Anne. I'm sure most of you are here to hear about New Horizons and Pluto and objects after that. But since you got both of us in the deal, we're actually a husband and wife team who do these occultations, I figured I'd spend about 10-15 minutes just introducing you to the type of work that I do. And if we mingle afterwards or whatever, or even right after the talk, you can ask me a question or two. So as was mentioned in the introduction, I'm an instrumentalist. I build hardware that goes on the backs of telescopes that flies up into the atmosphere. This picture just sort of summarizes better than anything else what I do. This is a group of people that I'm working with surrounding an instrument that we put together. This is a spectrograph that was built for the Sloan Digital Sky Survey to work in the infrared. I'll give you some details in just a second, but for the moment I just want to show you what the hardware looks like. This is a big thermos bottle. You see this enclosure, this big aluminum structure with a bunch of what looks like insulation on the inside, and then a bunch of stuff inside of that. What you're looking at is an instrument that has to be cooled to about 77 degrees above absolute zero, not to see its own glow in the infrared. And so the whole is that you're engineering a structure to contain an instrument and hold it at that temperature, and primarily for work at infrared wavelengths. That's what's motivated me all my life, is to observe the cosmos using the infrared part of the spectrum, where you and I are glowing like crazy at the moment. But of course, we're emitting no visible light, so it's a window into phenomena that you can't see with your eyes. And just to drive that home, I always like to point out two advantages of working in the infrared. One is what I just mentioned, that warm objects glow. I found this great picture of a dog, which is taken in the infrared part of the spectrum. And so you're looking at a map of the temperature of the dog. It's been sort of colorfully presented here, but to first order, what you see in that picture is brightness is a proxy for warmth. The brighter the image is, the hotter that particular part of the dog is. And of course, we all know dogs have cold noses. You'd never know that just, looking at the dog with your eyes. You might suspect it, and you know from experience that the dog's nose is going to be cold. But here is an explicit picture, using infrared wavelengths that shows that visually you can have access to this information if you have the appropriate sensors. On the right hand side, I've sort of mapped this to the sorts of phenomena I'm interested in that exploit that particular characteristic of the infrared part of the spectrum. And here we're talking about objects that are self-luminous because they're warm, but not hot enough to glow at visible wavelengths where you could look at them, with your eyes in particular. And so, for example, and I'll now show you a science example on the left, extrasolar planets, some of which are so fresh, so new, that they still retain the warmth of their formation. And although they glow, quite significantly at infrared wavelengths, they emit no visible light at all. And some of the first discoveries of extrasolar planetary systems were actually made in the infrared part of the spectrum, where the light from these planets was detected directly. On the left side, you're seeing a system known as HR 8799. It has 4 self-luminous planets, basically distributed almost like the distribution of our giant planets, a little bit further out. So like Jupiter, Saturn, Uranus, and Neptune. And in this case, that image is taken in the infrared part of the spectrum, mapped to visible wavelengths, so your eyes can see it here, but it's all a proxy for how much infrared light we see coming from this system. If you looked at this with the most powerful optical telescope on Earth at wavelengths your eyes could see, you'd only see the central star. The planets wouldn't be visible at all. The second advantage of working at these wavelengths is that dust is prevalent throughout our galaxy, and dust obscures our view of the galaxy. And you here in the southern hemisphere, have one of the best examples of that. When you see the Milky Way stretched out overhead at night, you see those mottled bands of dust that block your view of what is, the true spectacle of our Milky Way. Only about a tenth of the light from our galaxy at visible wavelengths makes it to our eye. Most of the starlight is blocked. The glory of the galaxy is not accessible to you at visible wavelengths. When you look in the infrared, as the image at the bottom shows, you see right through this dust to first order. Not completely through it, but through a substantial fraction of it, so that you're actually seeing the light from the majority of the stars in our galaxy. And you see the shape of the galaxy for what it is, a thin, flat disk of stars seen edge on from our perspective near the outer rim of the galaxy. And so one of the things that we do scientifically, going back to the right-hand side, with this particular advantage, is now that we can actually see the constituent stars in our galaxy, we can try to piece together what the galaxy looks like from our perspective inside of it. And this is an artist concept, but taking what we've learned now, looking through that dust, tracing the positions of the individual stars, we think our galaxy looks a lot like this. If I have a cursor here, I don't know if it'll come back. Yeah, if you can see that too. We are placed out here just outside of this bright stellar arm. And we know a lot more nowadays about exactly how the stars are distributed in the Milky Way, thanks to our ability to penetrate this dust at infrared wavelengths. Another science example of seeing through the dust, one of the things that really started me and my interests in astronomy professionally, is that we can look into regions where stars are forming. These are regions where gravity is collapsing clouds of dust, concentrating the dust as it builds stars and thus obscuring, your view of the forming stellar and around it planetary system. And as an example, here's the Orion Nebula. I think most of you are probably familiar with. It's accessible from this hemisphere as well. You can see the trapezium stars right in here, the 4 bright stars in the Orion Nebula. But this is the visible view, which, there's a real scarcity of stars. You look at that same region, that's the trapezium region again. This area is full of stars. It's a young stellar cluster full of thousands of stars, which are almost entirely obscured by the dust you see in the Orion Nebula. And so this is the motivation for building instrumentation like this, for enabling all these large telescopes we have to observe at these wavelengths in particular. So, the people who do this kind of work look at ourselves as enablers of science in some sense, creating the instrumentation that you can put on the back of a telescope to explore the universe in ways that you couldn't before. And so getting back to this picture and now getting a little bit more specific about it, this is a spectrograph. It's something that spreads out the light in the infrared part of the spectrum from infrared blue to infrared red in some sense, smearing out the light across all wavelengths. And I'll show you an example of a spectrum like that. But what's special about this instrument is that the light is fed into it by optical fibers. And so what you're seeing here, you can sort of see the individual fibers in the picture, 300 a row, so that each one of the fibers' light can individually be spread out into a spectrum. We can learn about the compositions, the velocities, the characteristics of 300 stars at once. Now you may ask, how do you get the light from 300 stars to go down those 300 fibers? Because the stars are sort of randomly spread out on the sky. In this case, we do it by drilling holes. So there's an aluminum plate on the right-hand side, and if you count the number of holes drilled in here, it'll amount to those 300 that map to the fibers. You can see a system of plugs, and the plugs are all different. The cables are all different colors, because in the case of the original Sloan Digital Sky Survey, humans plugged the individual fibers into each of these plates. And so for what has now turned out to be a couple million stars, people have been involved in actually doing the plugging of the plates every night, about a dozen of them, to take over to the telescope, plug them in, and then ultimately produce something like this. And so now each line from left to right across the screen is the spectrum in the infrared of a particular star. And this line at the top is just one star, but it shows a lot of absorption features in it. These are each coming from different chemical elements in the atmosphere of the star. Each one of these spectra can be analyzed to determine the chemical composition, the relative amount of sodium relative to iron, for example, or calcium relative to iron, or aluminum relative to iron. All these elements are in there. In the end, providing a fingerprint of the chemical composition of a star. And that's an interesting measurement to make, because that chemical fingerprint is unique to the environment in which that star formed. And nowadays, we think our galaxy was assembled in pieces, clumps of stars, whole galaxies of stars being fed into what is now the disk of the Milky Way and being assimilated into our star system. And these chemical fingerprints can actually trace backwards and link stars to the component which fell into the Milky Way, say, 5 billion years ago. And to me, that's fascinating, that we've actually created a field in some sense called galactic archaeology. It's not really archaeology, but it has the same sense that you can piece together the history of our Milky Way by digging into the spectra of the individual stars. And so that's the kind of an overview of what one of the instruments that I put together does. I can show you some examples for telescopes large and small of some other instruments. This is my favorite picture to show in general. It is the world's largest telescope. It's called the Large Binocular Telescope. It's in Arizona in the United States, and it consists of two 8.4 meter mirrors on a single platform. And the light from those two mirrors can be combined as if this was a single piece of glass, producing diffraction limited images at infrared wavelengths in particular. And so a few years ago, our lab and this graduate student who now works for JWST, he's been a close collaborator on the near-infrared camera, which has been a prominent instrument in the news as of late. Anyway, his graduate career surrounded putting together this instrument, which is a camera that takes pictures in the infrared, like of the dog, but in this case, coupled to this large binocular telescope to exploit its size and its capabilities. And so here's an example of what you can do with that. Not this. This is visible light images of Io, Jupiter's largest inner of the Galilean satellites, the 4 Galilean satellites. It is the innermost of those 4. It is a volcanically active satellite due to tidal squashing by Jupiter. And you can see the consequences of that volcanism looking at the disk of Io, and it doesn't look like most planetary surfaces. It looks more like a pizza to me. When Voyager flew by, and then later when New Horizons, the spacecraft Anne is about to talk about, flew by Jupiter on its way out to Pluto, it returned these images showing 3, at least, of those volcanoes in action, seeing the vast plumes that those volcanoes spew upward into space. At infrared wavelengths, you can think about what you might expect to see here. That is, each one of these volcanoes is a hot spot, a glowing hot spot on Io. And so if you take a telescope like the LBT with an instrument like the one I just showed you and look at Io, you see something that looks like this, which is a little confusing at first, but it's really the light from dozens of volcanoes, the brightest one right here. And this strange pattern is because, remember when I showed you that telescope, there are 2 mirrors side by side, one over here, one over here. We're combining the light from the 2. And when you do that with a telescope aperture, it produces a picket fence pattern in the direction where the mirrors, in the direction of the separation of the mirrors. And so that's why you see this picket fence. Each one of these volcanoes is producing an image like this. They're all much fainter. And it helps when you take the time to try to invert the image and ask, well, what was the underlying image that produced this pattern? This is it. And one of the things I like to point out is the image you're looking at here has about 3 times the resolution that the James Webb Space Telescope can produce. And that's just because of its immense size. The James Webb is only 6.5 meters across. We've got 23 meters working for us. So for this specific problem, you're a little bit better off than James Webb. Going from the largest telescope to the world to some of the smallest, one of my fascinations throughout my career has been trying to get science out of small telescopes. Why? Because they're in your backyard, literally, in many cases. That telescope is yours every night of the year. And so it opens the opportunity to do types of science that are impossible to do on the large apertures. On the large binocular telescope that produced that image of Io, maybe I can get access to that telescope 1 night a year. 8 hours sort of spread out through the year, but adding up to about 1 night out of 300. The picture on the screen is an observatory we have in our backyard at the University of Virginia, about 15 kilometers away, or 20 kilometers away. Sorry about the miles. I tried to make this all metric and failed miserably before I got here, but that's our fate living in the US. But we have some modest size apertures up there, about 3/4 of a meter, about 1 meter in aperture. And the key to making a telescope of this size scientifically competitive with that 8 meter or that 22 meter LBT is to put instrumentation on the back end of that telescope that's absolutely unique. And so for Fan Mountain, there's a lot of words on the screen, you can ignore them, but we had students at the University of Virginia design and fabricate an infrared camera for our 75 centimeter telescope, making it pretty much one of the only telescopes in that aperture range in the world with one of these cameras on the back end of it. It costs of order of $500,000 US dollars to produce an instrument like this. So you can't instrument small telescopes regularly with this, but this was sold as an educational project for graduate students that would ultimately lead to science, and it can produce some beautiful results. So these are images in the infrared of forming star clusters, and the reason I show them to you is to show why a small telescope can do big science. These images, represent clusters that were monitored for 40 nights over the course of about 3 months to look for stellar variability in these young forming stars. Young stars actually flicker quite a bit as material is added to them, as they rotate with spots, and as there's bursts of material falling onto their circumstellar disks. And with a giant telescope, you could never do this kind of 40-night monitoring project. With a small telescope, you can. So, there are examples here of applications of building infrared instrumentation from the very largest scales to the very smallest. My fascination with small telescopes led to my involvement in sky surveys. With a giant telescope, you're myopic. You're barely seeing with the best and largest instruments an area, the tip of your finger at the end of your arm. And to map the entire sky that way would take an inordinate amount of time. And at the same time, as I just mentioned, having access to the telescope for any more than a few nights a year is difficult. So if you want to map the entire sky, you do it with smaller apertures. And so I've been involved in a couple surveys, the 2 Micron All Sky Survey, as was mentioned before, with 2 1.3 meter telescopes, one in Arizona, the other in Chile. So you have to have telescopes in each hemisphere to do this from the ground, producing, with millions of separate images, that image of the Milky Way that I showed you a little while ago. Subsequently, I got involved in the Wide Field Infrared Survey Experiment, a NASA project to build an infrared telescope. It's behind me in this particular picture, giant thermos bottle containing a 40-centimeter telescope cooled to 7 degrees above absolute zero, making it sensitive in the infrared. Again, I mentioned briefly at the start, you're in the cryogenic regime for building any of these infrared instruments because the telescope is glowing, the detector is glowing if it's at room temperature. You cool all these things down to a few degrees above absolute zero, the glow goes away. Remember, the glow is a proxy for temperature, so if the temperature is down about absolute zero, nothing is glowing in the local environment anymore, and that makes you exquisitely sensitive to space. And that mission produced what is one of my favorite astronomical pictures of all time. This is the Heart and Soul Nebula. I think that's a more exclusively Northern Hemispheres thing. I don't think you have access to it, sadly, here. This is not what it looks like to your eyes. This is an infrared image where almost everything you see in this image is glowing dust. The greens and the reds are coming from interstellar dust, which in addition to being in the way and being in many ways transparent infrared radiation, can also emit infrared radiation of its own when it's warm, where warm here is about 30 degrees above absolute zero. So you're seeing the thermal glow from material just a few tens of degrees above absolute zero. You're actually seeing some stars. In the field, you see what look like ordinary stars. They look bluish because the mapping here is to temperature, and the hottest stuff is going to be blue, and even a couple of background galaxies shining through the dust down here. This is about, if I remember correctly, about 4 degrees wide, 2 degrees high. So this is coming up to a couple, 3 fingers out at arm's length of the sky. It's a huge field of view, and that is really the legacy of these sky surveys. What you're doing, it's cataloging all this information for the future use of the entire astronomical community, right? This is a legacy data set that then anybody goes into to pull up the brightnesses of stars, the positions of stars, images like this, and they do their science from the archive. And so these are enduring data sets that produce science over long periods of time. And so since everybody sounded somewhat excited about balloons before, I'll just finish by mentioning where my particular instrumentation interests are going right now, which is stratospheric ballooning. So NASA supports flights of instrumentation and even telescopes to altitudes of 30 to 40 kilometers. They do that by contracting these immense balloons. So it's hard to get a sense of scale in these pictures, but it's about 100 meters from here down to the parachute, which is right here. So this is a large mylar bag, very thin plastic. It's about 20 microns thick, and yet being 20 microns thick, because when it's inflated, it is about 100 meters in diameter. And so you can fit, almost an Australian rules football field inside of one of these balloons. And at 25 microns thickness, thinner than the plastic wrap that you put around food by a factor of about 4, the whole balloon still weighs about 2 metric tons and comes in a box that's the size of a truck. It's really an amazing thing. So it's one of the things that fascinates me about this is just the immense scale of everything. And in this picture, you see the balloon with a little bubble of helium in it. Why is there just a little bubble of helium in this immense balloon? Because as this thing goes up in the atmospheric density decreases. And the whole reason you're doing this is the balloon takes you above 99.5% of the Earth's atmosphere. So atmospheric pressure at the altitude where the balloon finally settles is so low that that original bubble of helium is now expanded to 100 to 200 times its size. And so now that balloon looks like this. And I think the most fascinating part of all of this is that that little speck right there is the experiment that this balloon is lifting. And it is about the size of, a large truck. And so the scale is just crazy. And we are in the process of putting together a balloon payload. So this is the little speck at the bottom at the University of Virginia. And so this is a near space telescope. It is a 0.5 meter in aperture. There's the telescope right there. It's in an assembly that's about 3 meters high and 2 meters across that weighs about 1,200 kilograms. And that's why you need this massive balloon on all that helium is you have to lift 1,200 kilograms off the ground and ultimately get up to 30 kilometers, floating off 99.5% of the atmosphere with very little atmosphere above it. And so maybe not in a nutshell because I got too enthusiastic and talked more than I planned, but you can tell how much fun I have with this and how much it motivates me and how much of a privilege it is to share it with you as well. But this is the type of instrumentation that excites me to work in the infrared. And I hope I've interested you 5% at least of how interested I am in this particular endeavor. Thanks.
Very interesting talk. Now, before we move on to our next talk, just want to see if anyone had any questions for Mike. No one's putting their hand up. Oh, we've got one. Pop over this way.
How long do you anticipate that balloon to stay up?
This is a long story, so you may regret asking that particular question.
We've got plenty of time. It's okay.
Okay, well, I don't want to go overboard, but there's an interesting aspect to the technology of these giant balloons, which is they actually don't hold the helium inside of them. They have vents, and these are called zero pressure balloons as a result. So you saw that small bubble of helium in there originally that expands the balloon out to full size, and it reaches the stratosphere or the upper parts of the stratosphere at 30 kilometers. Once it reaches that altitude, it begins to vent the helium. And so now there's an interesting interplay going on between helium being lost as the sun heats the balloon, and then night comes, and there's no more heating of the balloon. And at that point, because it's vented some of its helium, it doesn't have enough helium to stay up at its altitude. So it begins to come down at night. Fortunately, we bring with us about 300 kilograms of very finely ground iron. And we drop that as ballast at night. And that allows the balloon to maintain its altitude. But then the next day comes. And when the next day comes, you lose helium again. And you've run out of ballast. Now what are you going to do? You're going to descend. There's not much you can do about it. So the longest these zero pressure balloons fly is about 24 hours. And in fact, we would be really happy to get sort of a 12 to 16 hour flight to support our mission so that we fly for night, some fraction of the night. The other big issue is that once you're up in the stratosphere, you're carried by the winds wherever they take you. And we launched from New Mexico, which is fairly remote in the United States, but eventually you end up over Texas, or you could even end up over California. You get too close to a population center and they've got to terminate the flight. And that's, I didn't point out the parachute, but this comes down on a parachute, but it's 1,200 kilograms. It's coming down at a pretty decent velocity, maybe about 20 meters or 10 meters per second or so. So it can do some real damage even under a parachute. So you got to be careful about that. The reason it's a long answer, but I won't make it much longer, is that NASA and other organizations are exploring what are called super pressure balloons, where you seal in the helium. And you may say, well, why didn't you do that from the start? Well, it's actually hard to maintain that seal. It makes the balloon heavier, it can't fly as high. So they've been developing this technology for many years, and in the last 2 or 3 years, they've started to fly these super pressure balloons, which can come up or can stay up at altitude for 60 to 100 days. And so then, and this is the whole reason we're doing the project that's up on the screen, is we're exploring the possibility of building a near space telescope, something that would be almost Hubble-like in its ability to work independently of the Earth's atmosphere in particular. And if you could fly that for 100 days, you can start for very low cost. So Hubble costs multi-billions of dollars to maintain that mission. Each one of these flights and this technology, maybe a few $1 million, maybe a few tens of millions of dollars, if you wanted to build something that was larger. That's a tiny fraction of Hubble's cost. And if you could even do 10% of Hubble-like science, you would be coming out way ahead. So that's the long story. That was a great question because it addresses the key issue that's behind this particular project.
Great answer. I've got another question over here.
Just, I'm a ground-based person, so I don't want balloons. And so can you harness this machine to that large binocular telescope and look at some of these star-forming regions? And you mentioned Maray's work from Canada, that HR 8791.
Oh, yeah.
So I reckon there should be some more planets in there, and I guess with improved technology, would you be able to see if you can find any in those murky clouds?
This is so one of the things that having a large binocular telescope has enabled much larger surveys. I said it's kind of precious to get a night or two on that giant telescope, but when you have 20 or 30 people who collaborate together, they can each pool their resources. And so that infrared camera that I showed you, earlier, I don't know if I can get back to it really quickly. Maybe this is too swift, but the one that Jaron is standing next to, which we call the the mid-infrared camera for the large binocular telescope, the Elmer cam, we set up a 100-night program to survey for exoplanets. And what's interesting there is we looked at about 100 stars, found very few exoplanets, and the game is bigger than just finding another system and another exoplanetary system. You want to know how planetary systems form and how these large exoplanets form. And there's an interesting fork in large planet formation. They can form in one of two ways. A large gas cloud can collapse gravitationally and form a large lump of material, which ultimately becomes a Jupiter or Uranus or Neptune even. Not really, because the other mode that was the mode by which Jupiter, Uranus, and Neptune form is that you have rocky material that accretes to form a core first. And that core grows to large enough size where it can start to draw in gas and draws it in a runaway process that then mantles the planet in a massive amount of gas. That's Jupiter, right? That's how we think Jupiter came to be. With the probes we have orbiting Jupiter, we can actually detect the presence of that denser core down at the center. So for our solar system, at least, we know, Jupiter formed by this core accretion process, and the other giant planets likely as well. The interesting thing, I was about to say the cool thing and said, oh, that's a bit of a pun, because these two different formation mechanisms actually dictate the way the planets cool. The core accretion leads to a cooler initial planet and more rapid cooling. And for our technique, since we're looking at the planet's warmth, the rapid disappearance of those planets. They're there, but we can't see them. For the gravitational collapse, hot accretion, those planets start out a lot hotter and they stay luminous longer. And so the advantage of taking your big telescope resources and your instrument and looking at a large number of planets is that you can start to get at the statistics of how many planets should I have seen if I understand models of planetary accretion and the hot formation pathway was the predominant one. Or what if the core accretion cold pathway was the predominant one? And what we did with the 100-planet survey was show that it is much more likely that it is the core accretion, which you kind of expect, because it's what we see in our own solar system. And it's also the way we think we understand the planetary accretion process, that you start with a lot of gas that really just goes along for the ride, and dust grains, which do the sticking together and building up of the planets. So that's the way I look at it. It's not like, I want to find more planetary systems. It's, I want to understand the statistics of planetary systems and look at enough of them so that I can, draw conclusions like that. So hopefully that made sense. But, okay.
Wonderful. Great answers. Do we have any other questions? Oh, we got one last one, and then we'll get Anne up.
Just a quick question. How do you stabilize the payload on the balloon?
Okay, so now I didn't plan to any of these questions, but it's one I'd love answering because, okay, we are trying to achieve pointing with that telescope close to the diffraction limit of the telescope, which means about 1/4 of an arc second. So this is even more stable than astrophotographers require for doing deep sky images or whatever. And you think you're hanging under a balloon. How could you possibly stabilize a payload that's swinging back and forth and vibrating and all this stuff at the 1/4 arc second level? Well, you do it with layers. Okay, so if I zip ahead to this picture again, I hope I don't go off the end of the presentation. There. You can just barely see. Let me put my cursor there because it'll... There's a curved surface here, which is part of a large piece of aluminum. It's a disc that we spin. And so that's a reaction wheel, essentially. And you turn it one way, and it causes the payload to very slowly move in the other direction. And by adjusting its speed, you can adjust that axis. The telescope is on a bearing that, with precision, just allows it to go up and down in elevation. Those are two very crude ways of adjusting the orientation of the telescope. That would be in about 10 arc seconds of where you want to go, or about 50 times worse pointing than you need to do the experiment I just suggested. The last layer is the detector itself. And so there is an imager technology, a CCD technology, and you may know that on charge-coupled devices, the name of the game is dragging the electrons around by changing voltages. And the average CCD, all you can do is drag the charge out of a row and read it, and then drag the thing down and drag out the next row and read it, and so on. There's a class of objects that, it's a class of detectors, that was developed at MIT, which is called the orthogonal transfer CCD, which is while you are collecting the charge on the chip, you have the ability to manipulate the location of the charge. You can drag it up and down and right and left. And so we are compensating for that fine guidance by very rapidly, 100 times a second, measuring where the star is with a pick-off camera, where the telescope is pointed with the pick-off camera, and then dragging the electrons 100 times per second to a new location, the collecting image of the star, dragging that pile of electrons that represents the collected image of the star to the right location to continue to be underneath the star image. And so we're using an orthogonal transfer CCD to get down to that last arc second or even fraction of an arc second level. Good.
I think you answered his question. I actually was going to ask the same question, so I'm glad you asked it.
I'm glad you did too. Thank you.
Yeah. Oh, there you go. We got it answered. Now, we'll move on to our next speaker, Anne. And while I read out Anne's laundry list of accomplishments, she can set up her laptop. So Anne is an assistant project scientist for NASA's New Horizons mission to Pluto and the Kuiper Belt. She received a PhD in planetary science from Cornell University and has been a member of the science teams on NASA's Voyager and Cassini missions. Hardly done anything, have you? I wish my resume was like this. Where were we? She's also a research professor in the Department of Astronomy at the University of Virginia, USA, and her topic will be Beyond Pluto and Arrokoth. Did I say that right? There we go. What's next for NASA's New Horizons spacecraft? And she might actually give us a little bit of a rundown. I think Mike actually gave us a rundown on why they're here in Australia, didn't he? So you don't have to worry about doing that. You can focus on Pluto, because Pluto is not a dirty word. We like Pluto. Take it away.
All right, turn that back on. Hope we don't have, there was a little bit of feedback issue there. But thanks for coming out tonight to hear this, to those of you in the room, and thanks for those of you who are tuning in on a live stream. My name is Ann Verbiscer. I am an assistant project scientist with the New Horizons mission, working in Southwest Research Institute in Boulder, Colorado. So that's where I'm here from. And I'll talk a little bit more later about why exactly we're here in Australia. But I am a planetary scientist, and this sums up a lot of what I do. I do ground-based astronomy at different observatories around the world, using telescopes as small as the 40-centimeter one on the right to do occultation observations, to larger apertures. And as mentioned in the introduction, I worked on the Cassini mission, and I've also used the Hubble Space Telescope to do some of my work with other spacecraft space observations. So I work on New Horizons, and everybody loves launch. Oh, we can't hear the sound, but that's okay. You know what rocket launches sound like. But New Horizons launched on the 19th of January in 2006. How many people here have heard of New Horizons before? Yeah, most people. Okay, good. So it was a beautiful launch on a very cold day in January, but quite a long time ago. So this mission has been going on for quite some time. And that's pretty much ends. Whoop, keep going. So New Horizons has 7 instruments on board. It's intentionally a very small spacecraft, so it could leave the Earth very, very quickly. It reached the orbit of the moon in only 9 hours when it took the Apollo astronauts 3 days. And I guess yesterday was the anniversary of the Apollo 11 launch to the moon. Now, of course, the Apollo missions wanted to slow down and land on the moon, so it's not quite a fair comparison. But New Horizons got to the moon pretty quickly. It has 2 imaging cameras on it, LORRI and part of the Ralph instrument. It's also got an ultraviolet spectrograph and a radio telescope, which is basically the large white dish that you see there on top of it, and 3 other passive instruments for measuring low energy charged particles, high energy charged particles, and also a passive dust detector run by students at the University of Colorado. The whole instrument is very small, about the size of a baby grand piano, so not a large spacecraft at all when it comes to spacecraft that we send to the outer solar system. Can you hear me now? It seems like it's okay, good. Cassini, for instance, was about the size of a school bus, so very, very large. And New Horizons would be tiny in comparison to that. So in 2015, New Horizons reached its main target, which was the Pluto system. And these next few slides just summarize what New Horizons saw when it arrived. It basically revealed Pluto to us for the first time. Before that, Pluto was just a tiny little speck in a telescope. The best views came from Hubble, and they were kind of blurry-ish images. You could detect dark and light areas, but that was really about it. Pluto has one large moon, Charon, and here's an image from the spacecraft taken of Charon, and it also has 4 smaller moons, Styx, Nix, Hydra, and Kerberos, that New Horizons got various detailed pictures on because they were at different distances from the spacecraft when it passed by. Those moons were all discovered before New Horizons arrived, and New Horizons expected to discover new moons of Pluto, but didn't. That's pretty much it. No new moons of Pluto and no ring system either. So here is Pluto in all its glory. Some of the details of its surface, which vary tremendously from region to region. The geology on Pluto is just quite amazing. And this video highlights some of the diversity of terrains that you see close up with images from New Horizons. So it's really a fascinating place. I don't know if you could see, it's hard to kind of see the hazes above the horizon there that Pluto has in its atmosphere. Just wait till this finishes a bit. Looking at mountains on Pluto there, and on the right is the largest, brightest area of Pluto called Sputnik Planitia, which is basically a nitrogen ice glacier on its surface. Some of the colors here have been exaggerated a bit, but they generally trend toward the correct color. So some of those areas that look really, really red are really, really red. And the peachy color of Sputnik is exaggerated, but it gives you the general idea of what its color is. So everything would be a little bit more muted. And this is a view taken from, as you look at the disk of Pluto up at the upper right there, where the orange circle is. So if you were looking over the horizon towards sunset at Pluto, this was one of the last most detailed images that New Horizons got of the Pluto surface. And here I think you can see the haze layers much better. But as you look into the horizon there, you see the mountains in the distance rising above the horizon. And certainly we don't get views like that of mountains on the Earth. Those mountains are about the height of the Rocky Mountains in the US. And then I mentioned Pluto's atmosphere. As the spacecraft was receding from Pluto, it looked back at Pluto almost perfectly backlit by the sun. Not quite. This isn't a total solar eclipse, but the sun is illuminating Pluto's atmosphere all the way around, and it has a blue color to it. And if you look really carefully at one of these images, you can even see those mountains rising above the horizon. But after Pluto, then what? The mission was always designed to look at one object in what is called the Kuiper Belt. So the Kuiper Belt is what's sometimes referred to as the third zone of the solar system, where in the first zone would be where you have the terrestrial rocky planets close to the sun, and then outward from that you have the gas giants. The concentric white rings there show the orbits of the 4 gas giant planets, and then beyond that, beyond Neptune, there are just hundreds of thousands of icy, rocky bodies, much smaller than the giant planets. And the idea was to fly by one of these things. But when the spacecraft launched in 2006, such an object or target had not been even found yet. So the mission team was continuing to search for a flyby target for the spacecraft to fly by and look at closely after it flew by Pluto. So this slide here gets into little technicalities, but summarizes the small bodies in the outer solar system by their inclination, so how much their orbits are tilted with respect to the ecliptic that all the planets you're familiar with orbit on. So some of them are tilted at high inclinations, others are not at all, very right about 0. So they're very in the same plane as the rest of the planets. And then the semi-major axis is just the distance from the sun in astronomical units, or AU, where 1 AU is just the distance of the Earth from the sun. So 40 times away, farther from the sun that the Earth is, 60 times, 80 times, 100. So you see there are concentrations of objects right around 40 astronomical units from the sun. And that is really where the search teams were aiming. They wanted to find one of these objects that are called cold classicals. Now, it isn't cold because of temperature, like Mike was just talking about, all sorts of hot and cold temperatures. They're cold dynamically. Their orbits are very circular and they're not inclined at all. And the idea was that those objects haven't been bothered at all since the formation of the solar system. So they're really what we call pristine. They've not been changed in any way, and they basically exist where they were formed. A lot of these other ones in different colors, you see them in different places, and that's because they've had interactions with giant planets throughout the solar system's history. They've been thrown all over the place and tossed into different orbits, which bring them closer to the sun, and they get heated up and they change, their surfaces change. But the ones in blue, where we're really targeting, haven't changed at all. So what we found, so after Pluto here, this kind of summarizes what I was just saying. The goal is to visit another Kuiper Belt object after Pluto, which hadn't been found yet. The problem was the search area looks like this. So you need to find a moving target in one of those stars. And points of light, yes, is a star, not a KBO, but find something moving in there. Using techniques like Clyde Tombaugh used to find Pluto in the first place, blinking images to compare them and see if something moves. Well, imagine trying to do that with this. Really impossible. The search actually began in 2004 to try and look for a target, but the problem is that the target field is basically in the same plane as the Milky Way, right in the galactic center region is where you need to be searching. And it was unsuccessful. So something had to be changed to try and find something, because the spacecraft's continuing at 51,000 kilometers per hour on its way. You got to find something for it to look at. So we ended up having to use the Hubble Space Telescope, and the survey was started in 2014 to try and find something. I won't go into a whole lot of the details on what was found. Basically, 5 objects found, 2 of those tossed off immediately, and PT stands for potential target, left with 3. And as it turned out, the potential target number 1 was the one that ended up being the target, now known as Arrokoth. So PT1, those are the Hubble discovery images of Arrokoth moving in 5 different images. Those were the first pictures ever taken of Arrokoth. And originally it was given a nickname of Ultima Thule because that represented or meant beyond the borders of the known worlds. Also known as 2014 MU69. But those names have certainly have been dropped, and now the object is known as Arrokoth, meaning sky in Powhatan, which is a Native American language where the New Horizons team was based in Maryland. So afterwards, after the Pluto flyby, we did have to write a proposal to fly by Arrokoth at a distance of 3,500 kilometers on New Year's Day in 2019. That was the cover there of the extended mission proposal, which was approved. I still think you could have just written down on a blank piece of paper, fly by a KBO, and NASA would still have approved it. How could they not? But we did write a formal proposal anyway. So that mission has been going on now and is ending this September, the first extended mission for New Horizons. New Horizons has also been looking at other objects in the Kuiper Belt that you may recognize: Eris, Makemake, and Haumea, larger dwarf planets, just like Pluto. It has looked at some of those and is going to continue doing that in the extended missions coming up. But more about the Arrokoth flyby. It was a more challenging flyby than Pluto. Pluto, they had decades to plan and prepare every nanosecond of that flyby. And for Arrokoth, it was discovered in 2014, so really hardly any time to plan at all. But everything's really the same. You've only got one chance to do this, so you better get it right. And some of the complications are that you really have no idea whether this thing itself has moons or dust around it or a ring or anything like that. The sun is dimmer out there. And the communication time, it's going to take over 12 hours for a message sent to the spacecraft to get back to Earth. So everything is more difficult. So how do you find out more about Arrokoth before that flyby, before the January 1st, 2019? One of those ways is using stellar occultations. And those occur when a planet, asteroid, anything in our solar system passes directly in front of a distant star and blocking out its light, casting a shadow on the Earth. And as it turned out, immediately, once Arrokoth was discovered, we went looking to find occultation opportunities, and 3 turned up in 2017 and 1 in 2018. This is one of the paths of Arrokoth shadow on the Earth. Happens to be the one on the 4th of August, 2018. But if you recognize the date, the 17th of July, it was exactly 5 years ago today that third occultation happened for Arrokoth. So I'm sure many of you are familiar with stellar occultations, others may not. So this is just a simple cartoon describing what happens. This one is, for instance, Pluto. The starlight gets blocked on the Earth by a distant star. The Earth mostly moves and causes the shadow to move on the Earth, across the Earth. And if you put telescopes in different places, they see that shadow disappear, see the star disappear at different times, and that's what gives us a stellar occultation. So here's the part where I talk more about why I'm here in Australia right now. As it turns out, for another mission called Lucy that Southwest Research is leading for NASA, Lucy's going to look at 5 Trojan asteroids, or fly by 5 Trojan asteroid in the later part of this decade and early part of next decade. One of them is a binary called Patroclus and Menoetius, and there are 5 occultations by distant stars of the binary Trojan asteroid Patroclus and Menoetius that are happening just this month, and well, the first one was on June 30th, so in a very short amount of time here in Australia. And this illustrates where we were observing in both the Northern Territory and South Australia on June 30th, the date's kind of cut off at the top there, to observe an occultation by the Lucy target for another NASA mission. But on the 17th of July in 2017, this very night, we were in Argentina. This is the southern region of Argentina in Patagonia, with 25 telescopes, each one on each of those green lines there, to observe the occultation by Arrokoth for New Horizons. And this is a huge logistical effort. This is the same occultation team doing the 2018 event in Senegal. Lots of people involved. It's the leader of this effort at the center there, Mark Bowie. And we're all looking at results in Senegal after those observations. But basically, when the star disappears, this is the video of that happening from the Argentina event. You see, watch the star in the center, you see it, and then all of a sudden it's gone, and then it's back. That was Arrokoth passing in front of that star. So if you have multiple telescopes doing that, you can plot out the shape or silhouette of the object. And what we learned from July 17th, 2017, was that Arrokoth's shape was unusual, not a spherical object, but the actual shape could be any one of the three on the bottom row there. It could produce a silhouette like we saw. You could have a binary object, two objects separated, but it just the viewing perspective showed you that they look like they're together, but they're really not. It could be a contact binary, something just barely touching, or it could be a potato-shaped object, something very elongated. We just didn't know till the spacecraft got there. And this is I remind you to stop this just here and show some of the results that we had been getting with Lucy. That June 30th event produced these 4 chords on Patroclus and got a couple chords on Menoetius as well. There's the Menoetius, yeah. So it's for Lucy, just like for New Horizons, we're starting to see what the shapes of those targets are going to look like. And now I'll go back to resume the regularly scheduled programming. There we go. All right, so back to Arrokoth. This is a New Horizons image of Arrokoth on the 31st of December in 2018. We could see that from the occultation observations, we already knew that Arrokoth was about 33 kilometers along its longer axis, and that's exactly what New Horizons was measuring. But then the day after that, got better images on the 1st of January, and we started, since it was January in the northern hemisphere, we were saying it's a snowman, but in reality, the shape turned out to be quite different. But this is what a pristine Kuiper Belt object looks like, a cold classical object, about 35 kilometers long, and it was, as it turned out to be, one of the contact binaries, so 2 pieces just barely touching. That is apparently the result of a gentle merger. So this thing came together, these 2 pieces, very, very slowly and gently. And that is turning out to present a lot of constraints in solar system formation. Just how do you build something like this? And since it's the only example we have so far of what a cold classical looks like, we think this is telling us how the solar system formed and how pieces came together. But again, more on the shape of Arrokoth, you look at it from one side and you think, oh, it's a snowman, 2 spheres put together. But as it turns out, I have a model of Arrokoth here in my pocket. There's your snowman, but if you turn the snowman on the side, it actually turns out that Arrokoth is very, very flattened. And is it playing? There we go. So you tilt it over on its side, and it's actually more like a pancake and a lentil stuck together. Here's a view of Arrokoth rotating on approach by New Horizons. So you see the detail getting improved as we get closer and closer. But most importantly, with these occultations, the shape was exactly as predicted by the occultation observations on July 17 in 2017. The other advantage to not only figuring out how large an object is or how bright it is and what its shape is from these occultation observations, it provides exquisite astrometry. You know exactly where the object was at a certain point in time. And for New Horizons, that was very important because you need to know where to point New Horizons cameras. And we had one shot, as I mentioned before, at getting it right. So we had to take a big gamble and aim that camera for the highest resolution images in one place. And for a 35-kilometer object, getting it right in the center only happened because we had a successful stellar occultation on July 17 in 2017. And that enabled that imaging, which was the highest resolution. And it's not quite in the center of the image, but it's pretty darn close. Without an occultation to provide the astrometry you need to do that pointing, that would not have happened. It would have been cut off somewhere, or gosh, horrors, not even in the field of view. just to give a comparison, this is that early image of Pluto I showed earlier in the talk, and there is Arrokoth to scale. That's how tiny this little object is that we observed in the outer solar system. If you laid Arrokoth on top of Sputnik Planitia, that's how big it would be compared to Pluto. A bit more about solar system formation. The odd thing about this, or remarkable thing about this object, is that its major axes are both perfectly aligned, and that is highly unlikely to be due just to chance, and indicates that the lobes orbited each other before the two came together. And so we think that the gravitational collapse of a particle cloud, when the solar system was formed in a remote part of the solar nebula, this swirling collection of icy particles started to coalesce and form these two objects. Other pieces may have been thrown out to conserve angular momentum, and there could have been collisions with other bodies, or drag from nebular gas to shrink the orbit down and get them to come together very, very slowly. And they also don't look like they were damaged. There's no evidence of that on the surface at all. So it had to be a very, very gentle collision. So when you look at Arrokoth, you can think of it through New Horizons cameras as those cameras being a time machine that you can transport us to the early part of the solar system, showing us what these objects look like early, and what the building blocks of the planets were like early in solar system formation. So that ends the first extended mission for New Horizons. Now what's coming up? A second extended mission. Just in April, I believe, NASA approved a 2-year-long second extended mission for New Horizons. And now the spacecraft is moving on to bigger and better things. We would like to have another flyby of another KBO, and a search is underway to find a target, but so far it has not found a target for New Horizons. So the spacecraft has a plan, or the mission team has a plan to take advantage of its distance far from the sun to observe KBOs from larger distances than Arrokoth. It's going to look at as many as it possibly can to learn more about those other small bodies in that region of the solar system. It can also look at Uranus and Neptune at what are called high phase angles. So think of the phases of the moon and how it looks different in our sky in different times of the month. Think of being able to see Uranus and Neptune at first or third quarter. New Horizons will be able to get views of Uranus and Neptune that you cannot get from the Earth. It can also measure the solar wind interactions and measure interplanetary dust with its student dust counter out there. And it's going to do measurements that are more astrophysical, measuring the cosmic optical background. That is, how bright is the sky in between the stars? How dark is the night sky? And it has a suite of other science objectives that for heliophysics at NASA, and astrophysics, and planetary science. So the idea is to turn it into a more interdisciplinary science mission. But all of this is contingent on there not being another flyby target, because the second we find something that New Horizons could actually fly by closely, like it did for Arrokoth, then all of this other stuff would stop immediately, and all the fuel would be conserved, all the fuel that's left to do that flyby. So we're using ground-based telescopes right now, not Hubble, to do these searches. Mainly they happen with the Subaru telescope using its Hypersa Prime Cam, which is a very large camera imaging a large area of the sky. And we're using machine learning techniques to try and search for a KBO in those data, because it's a lot of images, and you saw what the star fields look like. So machine learning helps that a lot to sort through those results and those images. And we are also using a new filter that will allow us to go even deeper. Instead of, we're searching at the level of magnitude 26 right now, and we're trying to get to 26.5 for how deep these searches can go. And we had time earlier in June and had a couple nights at the end of June, and we'll be observing also in October coming up. So the search continues for a new target, flyby target, but until one is found, New Horizons does have important science that it can do. There is enough power left in the spacecraft to last until we've been saying the 2030s, but the engineers are working on that now, and I've heard they're trying to get it to 2040 as far as power goes. Fuel on board is a little bit more limited. We have enough fuel to redirect the spacecraft as much as 50 meters per second, whereas for Arrokoth, it was closer to a little over 100, about 120 meters per second. So we burned some of that fuel getting to Arrokoth. And of course, doing all of the science requires fuel as well. So it's all depends on what happens first, a flyby target found or all this other science, because the other science will use up the available fuel. So it all continues, and I'd be happy to take any of your questions that you might have. Thanks.
Do we have any questions? Oh, we do. I'll have to run around the other side.
Roughly how far out do you think it will get before it does run out of power, assuming it lasts as long as they're currently predicting?
Yeah, we can do the math on that, right? New Horizons travels at about 3 astronomical units per year. So we're talking, if the engineers are successful, that's another 18 years times 3. And right now, or when was it? I think it was April of 21. So last year hit the 50 astronomical unit mark. So we're about at 53, 54 right now. So I think it's about doubling that, isn't it? Yeah, close to 100.
Do we have any other questions? Yes.
Thank you, Anne. We have occasionally interacted with one another, either at DPS or...
That's right. That's right.
That's right, yeah. I remember at the last DPS meeting, it was an online one, Hal Weaver got really excited. He just found some what are called tight binary objects. And I was just wondering, has that research continued and refined the data a little further? And because they were quite intriguing, those objects. And everyone was excited by them.
Yes, that's correct. There has been a tight binary discovered in the distant KBOs that Hubble could not detect because they're so close together. New Horizons is the only thing close enough that can resolve those two bodies. They have about a 2-day orbit, something like that, 40 hours or so, something on that order. But since the imaging was done, unfortunately, the spacecraft's moving too fast. You can't look at it again. Yeah. So really, we pretty much have all that we can get out of it. And since it was just LORRI, you can't get any spectral information on the two of them, the two components. They are about, all we can do is assume equal mass binaries, about the same brightness. I think Hal pretty much got as much as we can get out of that. And he had another one that was a maybe possible binary, a couple of them. Now, the way we can learn a whole lot more about those is by doing stellar occultations, like we have been here in Australia. And there has been a paper written by my colleague Simon Porter listing several occultation opportunities, and several were for that binary. The problem is these sorts of efforts are expensive. It costs a lot of money to send telescopes all over the world and make that effort. And there just isn't really the financial support there to go out and get these occultations. But that could tell you a lot of information about those two objects and the others that we don't even know are binary or not.
Sure.
But since you find one and maybe two, it's telling you that the formation processes that early in our solar system, that binaries are commonly formed. And by looking at some of these other objects that New Horizons has had good looks at, that we're not sure whether they're binaries, but if we could get an occultation observation of them, maybe you could detect that. You'd have to have a lot of telescopes. It would not be it would take a lot of work, a lot of resources, both just real human power as well as money to do that kind of an event successfully. But the opportunities are there. Somebody's just got to be motivated enough to go and take advantage of them.
Well, thank you.
And I'd certainly be the first to volunteer. That'd be great. I wish we could do some of these.
We have another question.
Thank you very much for the talk to you both. The sort of description of the stellar occultation exercise kind of conjures up images of like an astronomical amazing race. Sounds really.
I feel like that sometimes, especially as Mike was pointing out, when it just sort of the plans happen on the fly. We wake up in the morning and we don't know where we're going and what we're doing. So
yeah,
it's different every day.
It sounds incredible.
So yeah, there's a lot of similarities.
So you sort of alluded to the answer to my question, I think, in the previous gentleman's question. But I was just curious when you showed that map, like a Google map image with all these place marks of where the telescopes had to be. So I'm guessing those aren't sort of fixed telescopes. People actually have to go with portable mobile telescopes.
Yeah, I didn't go into too much detail on the portables, but yeah, it's a portable telescope. We're using 11-inch telescopes this time. That are mounted on tripods. We usually had previously been using a lot of these Dobsonians. So I did show a picture of the one Dobsonian that we had most frequently been using up until this effort. But yes, portable telescopes at each site, and everybody drives to their respective spot. The idea is along those pink lines, put your telescope, each telescope gets assigned one of those lines, and you just go to where the skies are clear. Look at the weather forecast and hope for the best.
It's really amazing. Well done.
Yeah, it's a lot of logistics, and sometimes you're just at the mercy of drive times and weather forecasts and where you can get to while it's clear, manageably, realistically, safely. You don't want to fall asleep at the wheel.
A lot of places to drive in Australia, that's for sure.
We did 6,000 kilometers so far.
Hi, Anne. Look, two-part question. Firstly, do we know the composition of Arrokoth? And secondly, the merger, do we know how they stuck together? Is there something there like ice or holding the two pieces together?
Holding the two pieces. The assumption is that the interior composition of Arrokoth is water ice. I didn't mention the surface composition. New Horizons has on its Ralph instrument a LISA infrared spectrometer, which measures the composition of the surface of Arrokoth. Now, the resolution of LISA is not nearly what the LORRI camera is, the long-range reconnaissance imager, that gives you very high spatial resolution, but it's just at one, it's panchromatic, so no filters or anything like that or color information. But the infrared spectrometer does give you the surface composition information, and Arrokoth on its surface has no water whatsoever, amazingly, yeah. It's mostly made of, we think, methanol, and what is commonly called tholin. So tholin is an organic material that results from the irradiation of higher order organics like methane, and that gives it that reddish color. So that's about it. It really, many of these Kuiper Belt objects, even viewed from the Earth with an infrared spectrometer, just have these flat spectra in that range from 1 to 2.5 microns or so, where normally you would see things like water ice and other ammonia, other ices that we see commonly in the outer solar system. But many of these cold classicals are just featureless there, which is kind of frustrating. It doesn't tell you anything. It tells you what's not there, right? And Arrokoth spectrum was, I probably have it on a backup slide if I could find one. Showed a hint of methanol, and that was about it.
It's like hunting for asteroids, isn't it?
So, will it show it? Yeah, there. So that's, see what I mean by lower resolution. So you got these giant pixels, which don't show you much detail. And there is the spectrum. So those lines bobbling around from 1 to 2.5 microns don't show you a lot, but where the colored bars are, we think we see absorptions from possibly water, and the yellow one would be methanol. What we do see is on the left here, the tholins matching the spectrum of Pholus, which is another very red object in the outer solar system, and gives Arrokoth the very red color. And so, yeah, a little bit of evidence for the water ice and some organic molecules on the surface.
We have two
Thanks.
more questions from online.
Okay.
Terence is interested to know what the risk of hazards along the way. Is there any avoidance capability, or that it just get lucky that nothing makes contact at 51,000 kilometers an hour?
The New Horizons team approaching both Pluto and Arrokoth was very concerned about hazards, and even put together a hazard team to analyze the approach images for both flybys. So the hazard team for Pluto was pretty much in place for the entire month of June in 2015, analyzing the images coming in before the Pluto flyby to detect any kind of dust or rings or satellites that we didn't already know about. And they didn't find anything. And the same for Arrokoth. The hazard team was in place by Thanksgiving and spent all of December in the Applied Physics Laboratory in Maryland before the flyby on the 1st of January. And actually, one of my introductions into occultation observations was because none of the official New Horizons team members back in 2015 could come to Australia to observe a stellar occultation by Pluto that happened on the 29th of June in 2015. And I was here for that. I got to come. So,
Last one.
yeah.
Do you think we will ever discover Planet 9? Had to finish on a fun one.
That's a whole nother talk.
It is a whole other topic, isn't it? Yes. Well, what are your thoughts on there being a Planet 9?
Or, well, officially, what I'm supposed to say is we already know about Planet 9. Its name is Pluto. Right?
The other Planet 9.
The other Planet 9. Planet 10.
Planet 10. We'll
Planet
call it-
X.
Yeah, well, it has been known
Planet
as Planet
X.
X, hasn't it?
Yes.
Yeah.
Okay. So there is observational evidence that objects in this distant regions of the solar system are only observed in one area and not another because of the gravitational influence of supposedly a large planet that we haven't seen yet or found. That is the view of the people that are looking for Planet 9. And there is a contingent of astronomers, ground-based astronomers, that also look at the same data and say it's observational bias that is making it look as though that's the way it is, and that there is this Planet 9 or 10 or whatever its name is. So the groups they don't agree, right? And until the object is found, of course, that would settle things. But as far as my own personal opinion, I'm not heavily involved in that research, but I'm not inclined to think that there is this large object. It does seem to be like it's a case of observational bias, but I don't know the specific enough detail to really give that much of an intelligent answer.
Well, thank you very much, Anne and Mike, for tonight. It's been wonderful. We've had some good questions. We've learnt a lot. I've learnt that.
Thanks for coming. And before you leave, I have, I'm sorry I don't have any New Horizons stuff with me, but I've got Lucy patches and pins. If you'd like to take one, please do.
I'm going to have to grab one of those. But thank you very much.
Right.
Thank you, everybody, for joining us.
Thanks.
It's been a wonderful
Great
evening.
questions. Thank you.
I also just quickly want to thank Lee for last-minute setup and dealing with me pressuring him to come here. He's doing a great job. He does a great job
thanks for all the
every stream. So
support.
just want to give him a shout out for that. Thank you, everybody. Thank you, everyone, for watching at home. And we'll see you, I think our next stream is in about 2 weeks' time back at Miller Hall. And now we just wait for Lee to cut it.